Hey students, I thought I'd make you a solution guide to exam number one, and this way you can kind of run through it and do two things. Number one, you can kind of self-grade because it'll take me a while before I can grade everybody's, and so this will give you a chance to kind of self-grade. But better than that, it'll give you a chance to kind of pinpoint your mistakes and hopefully learn from them as we go forward here. All right, so with that in mind, let's look at number one here together. I'll just put number one. Here's the exam. Here's the question. It says, an electron is released from rest from the center of a negatively charged ring, and it gives us the radius. When the electron is displaced slightly, it moves along the x-axis. What is the speed after it has moved really far away? So I'm hoping this first part A is pretty straightforward to you. And then it'll give you kind of a pattern on what to do on the harder one, B. Let me hold off on reading B here. But hopefully in your mind, you're doing, something like the diagram I gave you in the lecture that, the way we attack our electrical problems is we find the electric field. From that, we get the force, we get the acceleration, the velocity, and the position, or we get to velocity from conservation of energy. And that is the approach on this one. In fact, now that I think about it, let me just kind of open the book because this was, I think, well covered in chapter 25. That's where we got electric potential. And there's a problem that I did in the lecture. It's 59. Here it is. It actually begins on the bottom here of this page. And it says x-axis of symmetry, charged ring, radius r, charge q, particle of mass m, charge q, and they even give a little picture on the next page. And this is exactly our problem. And so here's the velocity. So we did this one. I suppose in theory, if you remember the derivation of all this, you could just go back and plug this in. But that's not the intent of this problem, or any physics problem, is to memorize a bunch of equations, but it's to go ahead and work that out from scratch. And so that's what I'm going to do. Now, one of the things that we could either rederive or come back to is we did a lot with the ring. And so here is example number 5, where we have the ring, and of course we worked out what is the potential from a ring. And that's really where I want to get started here, is that I would start this problem by saying, okay, what is the potential from a ring? And I would just kind of look at that problem and go kq x squared plus a squared. Now, of course, if you don't remember it or remember that we did it, you can derive it. The fundamental idea is that the total voltage is the sum of the voltage from a bunch of points, and the potential from a bunch of points is Coulomb's constant dq over r. And then if you look at a ring off at some distance x and radius a, then all the points on that ring are the same distance r away. And so r can be brought in front of the integration symbol. And then you just get k, where q then is the charge of the ring and r is the distance away. And then using Pythagorean's theorem, it would be x squared and plus a squared square root. And so that's where this comes from. And so either derive the potential yourself or look it up on the example problem we did. But all of those hopefully look familiar to you. And so the idea here is I could say, what is the initial potential? And the initial potential would be Coulomb's constant times Q. And if we were right at the center, the X would be 0, and that would just be an A. And the final potential is when it has moved really far along on the x-axis, go to infinity, if you will, which means that one would go to 0. So if I put in my numbers here, 9 times 10 to the 9th, and the charge is a negative, what was it again? Negative 11.5 nanocoulombs, all over 0.1. The 10 to the 9, 10 to the minus 9 cancel off. We grab a calculator here. In the top, we would have 9 times a negative 11.5 divided by a 0.1. And we're looking at a negative 1,035 volts. So the change in potential, which is final minus initial, would be 0 minus a negative, and that gives us a increase of 1,000 volts, 1,035 volts. And of course, the reason we care about that is because the change in potential is the charge times the change in potential. And the charge is an electron, so negative 6.02 times 10 to the minus 19 coulombs, and times a plus 1,035 would be the change in potential energy here. Okay, so I'll just take, well, that number there, negative 1.602 times 10 to the negative 19 times a positive 1,035. And we're looking about a change in potential energy of a decrease. That's good, because we want to increase our kinetic energy. So negative 1.6, actually let me go 66, round it, times 10 to the negative 16 joules. And the change in kinetic energy is the opposite, the change in potential energy, so that's a positive 1.66 times 10 to the negative 19 joules. And that has to equal the work, which equals the change in kinetic energy. Oh, well, I already said that. And so that would be 1/2 mv final squared minus 1/2 mv initial squared. And I'll just cross out the initial because that's 0. Initial speed is 0. And so then we're going to have a final speed of, and I can take that energy, let me take it with a positive number, so let me do that. And then I'll multiply by 2 and divide by the mass of the electron. So that would be the velocity squared. Then I'll take the square root of all of that. And it looks like I get a speed of 1.91 times 10 to the 7, it looks like. 1, 2, 3, 4, 5, 6, 7, yeah. Meters per second. So, yay, there's my speed. And well, like I said, that's kind of our straightforward one. Hopefully that went really well for you. And like I said, hopefully you didn't have to do as much work as I just did. Hopefully you just kind of remembered that from class and from the examples. We used it a lot in conservation of energy. Now, the harder one then is part B here. And we need to get the potential from a ring. And a cylinder, which I'm going to think of as the sum of the potential of a bunch of rings. And so we're going to have to integrate that. And that is kind of the main point of our calculus, as well as our chapter 23 and as well as our chapter 25. In fact, this totally reminds me of one of the problems. I believe it was 54 in this chapter. And again, not a easy problem here, but it does say here is our cylinder, or they call it a cylinder shell, total charge Q. And we're asked to find the potential from this. Now, this was not an assigned homework problem, although the other one that's very similar to this was number 28 and 23, and that was where we found the electric field from a cylinder. So if you know the electric field from a hollow cylinder, great. Chances are you don't, and that was the whole point, that you would say, I'm going to integrate, and I'm going to go back to my equation for a ring, which was Coulomb's constant times the charge, and I'm going to put the charge on the ring, divided by the square root of a squared, being the radius of the ring, and x squared. And so if you draw a little picture here, and you kind of imagine yourself, and I guess I didn't actually read the problem here with you, but it says, as in part A, an electron is released from rest along the axis of symmetry from a thin-walled, hollow-charged cylinder. It is released from the beginning or the edge of the thin-walled hollow cylinder. The cylinder has a total charge of, its length is 25 centimeters, and it still has the same radius. The electron is pushed along the x-axis. What is its speed? So it's going to start here and get pushed away. So I'm going to think of these as a bunch of rings. Now you can imagine that each ring then is a little further away, and that's what we're going to be adding up. And so if you wanted to know the potential, you would be saying that, okay, I'm starting with my first ring, and I guess I would say this would be the initial potential. And so my x would be 0, so I would have an integration from x equaling 0. And then the last one would be a length L away, and it would be Coulomb's constant. And here's where I'm going to have to give a little thought to this dq. If I slice these into a bunch of rings to add up, then I could say there is a charge per length on each ring. And so it would be like a dq on each ring divided by the dx, the charge per length. So I can write this as a lambda over dx, and that would be my charge on my ring. Let me use the same symbol, capital Q. And that's an important step, to change the dq to a dx so I can actually do the integral, because I know the limits of my integral from x equals 0 to x equal L. But I'm going to need to know the charge on each ring in terms of x, and that's what this is for. In fact, since it's uniform, we could say it's the whole charge on the cylinder divided by its whole length. And that's nice because this Coulomb's constant, as well as this charge density, can be brought in front of my integral. And so now I have a pretty straightforward integral to do in terms of x, which clearly is screaming at me trig substitution. But as you heard me say in the lecture, and I'll say it again here, we probably should focus our time on physics. So go ahead and either look it up since you got open notes, and I'll just jump to the back of the book here and go to the calculus section. Looks like the one I would want is right here. The integral of dx divided by the square root of x squared plus a squared. Looks like it's a natural log of x plus the square root of x squared plus a squared. So that's the one I'm going to use here. And then say this is kq over L. And then this would be the natural log of, maybe I'll just write it out, x plus square root of x squared plus a squared evaluated from 0 to L. So this would be kq over L, natural log. And then if we put in the upper limit, we would have L plus the square root of L squared plus A squared. And then we would have minus when we put in a 0, which we've put in a 0 for x. Those go away, and then you just get an A. And then if we use the property of logarithms, when you subtract two logarithms, that's the same as a quotient. So now we can actually calculate the initial potential. Now, going back to our part A, what did I do with that part A? All the charge was on a single ring right here, and we got 1,035 volts. So thinking about all that charge now being spread out, it's going to be a little bit further away, so I expect this to be smaller. So this number better be under 1,035. Maybe it would be the equivalent if I had the ring like in the middle, but it's not a linear function, so it wouldn't be exactly that, but we could probably do a ballpark calculation. But let's just put this now into our calculator. Maybe I'll start here. I'll do the L squared first, because that's the 25 centimeters, which I'll put in terms of meters and square it, and add to that the 0.1, square it. So there's that term. Let me take then the square root of all of that. Let me then add 0.25. Let me divide that by the A, 0.1, and then let me take the natural log of all that. Okay, so all of this is about a 1.65. So now let me go ahead and multiply by the K, 9 times 10 to the 9th. Let me multiply by the charge that's on this whole cylinder. That was the negative 11.5 nano. Let me then divide that by VL. Okay, now, can't remember, did I actually do the answer? Yeah, so the answer times 9 times 10 to the 9th, 11 times 10 to the minus 9. I better double check. Yep, because that same charge, length 25 centimeters. Okay. So all that's looking good. And I get a negative 682 volts. Good. Kind of happy with that. It's still negative, and it's way less than the 1,035. Not quite half as much, and so looking good. Now, there's no point in working real hard of getting the final potential, because the final potential is going to be adding up this same equation. Thinking of ourselves when the electron is super far away. See, because now I just added up the rings when it was, right here, initial. But final, I guess I'd be viewing it something like this. Here's my cylinder, and I'm way over here somewhere. And in the limits that x goes to infinity. So this summation is an integral of a bunch of zeros. I'm so far away that the potential is 0 from every little ring. And so if you add up a bunch of zeros, you get 0. And so that one we probably don't even need to think about in terms of what's the final potential. So the change in potential, which is final minus initial, would be the 0 minus the negative 682, which is a plus 682 volts. So the change in potential energy, which is Q times the change in potential, would be the negative 1.602 times 10 to the minus 19 times a 682 volts. Now, which is going to make, so I'll take that number, make it now a positive number. Then multiply by a negative 1.602 times 10 to the negative 19. And that is a decrease, negative 1.09 times 10 to the negative 16 joules. And so the change in kinetic energy, which is the opposite of the change in potential, then becomes a plus 1.09 times 10 to the minus 19 joules. And again, going back to part A, we got this number, 1.66 times 10 to the minus 19. So we have less energy. It makes sense because our charge is not as close to push it away and doesn't give it as much push or as much work and as much velocity. But the same idea, this is going to be 1/2 mv final squared and 1/2 mv initial squared. The initial we can ignore. And so if we take this to be our kinetic energy, you need to make it positive. We can multiply it by 2. We can again divide by its mass. That would be the speed squared. We should take the square root, and we should get the speed a little bit lower because there's not as much energy here to work with. And sure enough, we get 1.5, and it rounds to a 5, times 10 to the 7th meters per second for the final velocity. Nice. Good problem. Maybe a hard problem. At least B is hard. So hopefully I gave you an easy one on A. And you kind of see that pattern. Hopefully the next one's the same thing. Easy in A, a little harder, a little more advanced. Let you think about part B here. Okay. But there is our first our first problem, a part A and a part B. But hopefully part A helps you do the harder one with part B. Okay. Let me grab another pad of paper here. Looks like I finished up that one. Let's jump over then to problem number 2. Now, problem number 2 says, the spherical capacitor. So we're talking about a capacitor. This would be chapter 26. We have the inner radius of the outer conductor at 2 millimeters. We charge it to a negative Q. The smaller conductor has a radius of 1 millimeter and has a charge of Q. The space between them is filled with mylar. Find the capacitance of this device, and then a B. Well, let me just start with find the capacitance. And again, you could do it, I guess, the short way or long way. I guess the short way is maybe the easy way, but we did this one. We did it in class. Also did it in your book. Let me just grab the book here and going to help you turn to chapter, let's see, 26 is where we got to capacitance. And the first one we did was the parallel plates. That's kind of the most important one. Second behind that is the coaxial cable. And then third from that was this spherical one. In fact, this is the same picture. And so here is the picture that I put on your exam. Here is the same wording, and ultimately then on the far page, so this is example number 2, is then we have this equation for the capacitance. So the fastest way to do it is just to use what's already been derived and then continue on with the problem. So I would encourage you to do that. I would encourage you to say, hey, we did this one in class. Let's work this out. If you want to work it out, you can. Let me do that here. Let's see. If I wanted to work it out, the first thing I would do is, okay, what's the voltage difference between the inner and outer? And so I would do, and I'll do absolute value. Technically, there's a negative in there, but I'll kind of ignore that. But I would add up the electric field. This is our definition of potential difference. And we learned that the electric field between them, or outside a sphere, is the same as a point. So this would just be Coulomb's constant times Q over R squared. And I'll just drop the negative sign since I'm doing absolute value, dr. And I'm just going to do an integral from A to B. And so then this just becomes Coulomb's constant times the charge on that inner conductor. And when I integrate 1 over R squared, I get a negative 1 over R evaluated from A to B, which is then Coulomb's constant times Q. And I guess it would be a negative 1 over B minus a negative 1 over A, and something like this. Now, maybe to simplify it a little bit, I might get a common denominator, AB, and then so that would be a B, and that would be minus an A. And then to get the capacitance, it would be Q over the voltage. So that would be Q over this crazy thing, which is KQ B minus A. And then when I flip and multiply, it's AB. But the point is the Q's cancel off, and you get A times B, Coulomb's constant, B minus A. And that is exactly where you probably should start this problem. So you're not having to derive it. But of course, what I just did is what we did in class, as well as there it is right there. These are all the steps I just did in order to get the capacitance here. All right, so whether you do it, I'll call it the long way and rederive it, or kind of look up from your study material, there is the capacitance from a concentric capacitor, spherically concentric spheres. Yeah. Okay, now that's not the only part to this problem, because what we just went through in that example, number 2, where this came from, was free space. So that's why I'd say you're okay to start here, because really this problem is to take a capacitor of free space and then add a material. And so we wrote it this way, that the dielectric constant, kappa, times the capacitance of free space is the new capacitance when you have some material. And that's really what this part A is centered upon. Part A here is centered upon, okay, you already know the capacitance when it is filled with air. What happens now when we fill it with, and I forgot what we filled it with. What did it say? No, I've lost my sheet that had the test on it. Okay, the notes are around there somewhere. Well, this is not it, but it's the same thing. So, okay. Mylar. Yeah, Mylar. See, this is really what this problem is about. See, here's where in the book it starts talking about adding some sheets in here, and it shows us somewhere, right here, that the new capacitance is the dielectric constant times the old one. And then if you turn the page, there's a nice little table right here. And we can look at Mylar, and it has a dielectric constant of 3.2. So really that's the idea, is 3.2 times the capacitance when it was filled with air. So let's just do the math when it's filled with air. This was 0.001, because it was 1 millimeter. This was 0.002. Then we're going to divide it by Coulomb's constant, 9 times 10 to the 9th. And we're also going to divide it by the difference between them, which if this is 2 and this is 1, that's 1 millimeter, so 0.001. Okay. And so we are looking at 2.22 times 10 to the negative 13 farads for the capacitor when it is just filled with air. And so if we multiply it by 3.2, we get 7.11 times 10 to the negative 13, at least in scientific notation. If we switch to engineering unit, the 10 to the minus 12 is pico, so then we'd have another minus 1 to go here, so that'd be a 0.711 picofarads. And so that would be the capacitance then when it's got the Mylar in it. And so that's what A is all about. Now, in B, we're going to go to this same idea, whereas filling it with Mylar, it's not a bad idea because it increases the capacitance, but it says it has a limiting factor of about 7 million volts per meter for the electric field. So the electric field cannot exceed that. And I should say cannot exceed that anywhere inside. And so if we go back to our equation for the electric field, Coulomb's constant times Q over R squared, you can see that the field varies depending on where you are, and it must be the strongest right here at the smallest radius. And so in other words, we get the maximum field when we are right at radius A squared. And then also from the chart here, which is called the dielectric strength, here says it cannot exceed, so the electric field must be less than, I'll even say equal to, 7 million volts per meter. Now, I hope this looks very much like the practice problem. The practice test had one just like this. In fact, now that I think about it, there's also one that is in the problems. In fact, the one on the practice test, and the one on the book here. Here it is, number 45. It uses a coaxial cable. In fact, the one on the practice exam is an exact copy of this problem. It has the dielectric constant. Numbers might have been changed on the practice exam. I'll have to look, but I don't think so. I think this was a long time ago. And as you can see here, a lot of the problems I give are directly straight ones. Are examples from the book, or examples I did in class, or ones right here on the homework. These problems aren't easy, but hopefully you recognize all of them because they're right out of the book. Okay, so this one, like I said, is the same structure, just the geometry is different. We have spheres instead of a cylinder here. Okay, so that being said here, then I could go ahead and do something like this. I could say then that KQ over A squared must be less than, so I'm just doing a substitution for what does the maximum electric field equal that, must be less than or equal to 7 million volts. Yeah, I'm just debating what direction I should go. Why don't I just do a Q then? So this says Q on our charge capacitor must be less than or equal to. And let me put in some numbers here. So we'll put in the 7 million. I'll put in the A, 0.001 squared. I'll then divide by Coulomb's constant. And this says that our charge must be 7.78 times 10 to the negative 10 coulombs or less. Because if we get greater than that, the field on the surface of the inner conductor, where the field is the strongest, will exceed the strength of the material. The material get ripped apart, and then, no more material. We'll have a little fire going on here. Okay. Well, maybe, hopefully not a fire, maybe just a little pop and explosion, and hopefully just kind of fun, nothing serious. But it, like I said, can get problematic. Now, I'm not done here because we really want to get the voltage. So there's a couple ways we can do it. Probably at this point, the best way is to use capacitance, charge, and voltage. That is, then the voltage is charge over the capacitance. And of course, then we can view this as just an air-filled capacitor or a dielectric field one. You might have noticed then that in this little bit of the equation or of the problem, I treated it as if it was an air-filled one. If it had Mylar, I'd have to put a kappa in here. And then that would make this a little, the Q, the kappa would move to the other side. And so this would be a little bigger by kappa. But then the capacitance would go up by kappa. What I'm getting at is we could do it with air-filled, so I'll put a little knot there, or we could do it with filled with Mylar. And they're going to be the same number because this number is going to go up by a factor of kappa, and so is that number. And so the ratio is going to be the same. So it doesn't really matter how you think about it, but I just realized that I did the equation for the field as if it was air. So let me do the capacitance as if it was air also. So knowing this is the maximum charge, the 7.78 times 10 to the minus 10, when it is filled with air. Let me come back to part A where I got the capacitance. When it was filled with air. All right, so I already got that number still in my calculator. Actually, I also have this number, which is the capacitance of the air. Let me just copy and paste it. And I get 3,500 volts. So the maximum voltage is 3,500 volts. Yay! Anything more than that will tear the material apart. And of course, it'll tear apart right on this surface first, because that's where the field is the strongest. But it doesn't matter where it tears apart. Once you tear it apart, it starts a little smoke and fire, and pressure builds up, and this whole thing hopefully just pops, goes. And they're all designed that way. They're not made real tight purposely so they don't explode on you. There's pressure just builds up and pop. And you go, oops. Did something wrong there. All right, so there is the first two. And again, hopefully those look familiar. And like the homework to you. And you can kind of see, kind of showing you in the book where this is, because again, I want this to be a learning process for you. And so, what did you do wrong? And you can hopefully see right there in the book where we can fix it or correct it. Okay, let's try number 3 here. Number 3 is a little circuit here. It says, what is the charge on each capacitor? What is the voltage across each capacitor? And what is the energy stored on each capacitor? All right. And so the lesson that we hopefully learned here was this equivalent capacitance thing. In fact, as long as I'm showing you the book here, why don't I look at chapter 26, and I think it's example 1, 2, 3. Oh, here's 4. Here it is, example 3. So example 3, they're saying, look, this is how you solve a problem. You look for things that are in series or parallel. You make the equivalent until you take a circuit that's got a lot of capacitors and you simplify it. And you might or might not need to simplify it all the way down to 1 capacitor, maybe just to 2. I think that's going to be the case for us. But let's see what we have. And so let's study this circuit a little bit better. I hope kind of the first thing you see is that the 1 and the 5 are in parallel with each other. And when parallel ones, you just add it together. So that's the equivalent of a 6. So I might do this. I might say, let me leave the 3 alone, and let me replace the 5 and the 1 with a 6. Now the 4, I'll leave it alone also for just a second. And I'll just kind of leave little knob here. That's what's hooked to the 24 volts. But this is equivalent to this, and this could help me solve for what's going on here in the real circuit. Because hopefully the next thing you notice is that the 3 and the 6 are in series with each other. And so the equivalent of that one is where we do the reciprocal sum. So 3 reciprocal plus 6 reciprocal, enter reciprocal, that gives me a 2. So this would be equal to a 2, and a 4. And of course, that could be equal to a 6, but I'm going to stop there because remember, this then is hooked to 24 volts. And if these two are in parallel, they have the same voltage. That is, this whole 24 volts. And in fact, to be quite honest, we could have just noticed that way back at the beginning one, that if you take this loop right here, you have to increase the energy of 24, so you have to decrease of 24. Now, maybe I'm getting a little bit ahead of ourselves in our circuit analysis, but this one has 24 volts on it. And then this whole series of the 3 of them, which is the equivalent of that 2, also has 24 volts. But if we remember that capacitance is equal to charge over volts, here we know the voltage of this 4. In fact, maybe I'll just put it in here. Here's the 4. I know the voltage is 24. And keep in mind that if you ever know any 2 of these, you can get the third one. And so if you multiply these 2 together, so 4 times 2 is 890, is that a 96? And so this is 96. And so there is my charge and the voltage on what I'll call the easiest one. Now, the harder bit is what this number 2 represents. But if we just do this, that Q is equal to capacitance times voltage, and we take this capacitance as a 2 and the voltage as a 24, we get a 48. So this has 48 on it. And of course, that's only useful as it helps us back here. But keep this in mind, that if I take this and go back to its equivalent, that means 48 comes out here and goes on this 3, and then 48 goes on this 6. So that tells me right here, the 3 must have a charge of 48. It also then tells me that this 48 going on this 6 means it separates out, and the 2 of these add to 48. And so maybe I'll make a note of it and say, okay, now these 2 right there should add to 48. Okay. But before I go any further to the 1 and the 5, let me just remember right here that then these 2 can give me that third one, right? Because then voltage would be charge over capacitance. So if I go 48 and divide it by 3, what is that? 1, carry 1, 18, 6. So this would be 16 volts here on this 3. And that's great because, again, kind of looking at this whole loop here of the equivalent, this is the advantage of looking at equivalent circuits, 24. If this is an increase in 24, and the way I like to say it, somebody went for a little hike, they'd go up 24 this way. They have to, if they go this way or a buddy goes this way, they have to go up 24. And you just told me that's 16. So that means that has to be 8. And better still, that 6 is the equivalent of these two. These have the same voltage. So each of these must be 8. So the voltage on the 1 is an 8, and the voltage on a 5 is an 8. Which, as we said before, you only know 2 of these, you can find the third. And so Q would be these two multiplied together. So if I go 1 times 8, I get 8. And if I go 5 times 8, I get 40. And then these 2 should add to 48. Yay. And if we check our conservation of energy and conservation of charge, we can see then that our charge comes, the 96 comes out here and goes on to here, and then another 48 go on to here. And so what total comes out of the battery is this two added together, which is 144. And I didn't do the equivalent of these two, but if I did, it would be a 6 connected to a 24. And so the charge would be 6 times 24, which is 144. So, awesome. 144 is exactly what I want to look at here. And it does match this. And then, of course, this 48, which came on here, goes and splits, and so those two add up. So that's great. And in terms of energy, going around or going for a little hike like right here, if I went this way, I'd go up 24. That means somebody going this way must also go up 24. And so the voltage on number 4 must be 24. And somebody going this way could go across the 5 and then the 3. So that should, the 5 and the 3 should add up to 24. So the 5 and the 3, good, should add up to 24. Or going this way, somebody takes a hike and goes over the 1 and then over the 3. That should also add to 24. So the 1 and the 3, it adds up to 24. Okay, good. So everything seems to be matching really well, so I'm feeling real comfortable with all that. Nice. And if I'm comfortable with all that, then the energy is just 1/2 CV squared. And so I'll just go ahead and say 1/2 times a C times AV squared gives me 32 microjoules of energy. 1/2 times a 3 times a 16 squared gives me 384 joules of energy. 1/2 times a 4 times a 24 squared, where most of the energy is 1152 microjoules of energy. And 0.5 times 5 times 8 squared would be 160. Now, if you wanted to kind of test to see if this is right, we could add up all this energy. So there's 160, there's the 152, there's the 384, and then there's the 32, and all of this is 1,728 microjoules of energy. Nice. Now, to see if that even makes sense, we can go back to this equivalent one. This equivalent of all of these would be just a 1/2 times its equivalent capacitance of 6, and the voltage applied to it is 24 squared, and its total energy is 1,728. So all this could be thought of as just one capacitor. This is equivalent to the whole thing, and therefore there is, whoops, that's the whole charge. There is the whole energy. Oh, I guess it's in my calculator right there. And so they match. And so on this type of problem, I would feel really good that, hey, I'm doing it right. Conservation of charge works, conservation of energy works, and then the overall equivalent conservation of energy works perfectly too. Nice. And so hopefully that all makes sense. And again, if you didn't get it all right, hopefully you've learned something here a little bit. And you're not much ready for the next exam. All right, well, let's try number 4 here. Number 4 looks like we've got a force between two charged particles. And again, like a lot of these problems, we'll kind of have the basic idea in part A and then expand it a little bit into part B. But here we have a small upper charge, and it's a distance away from a bigger lower charge. What is the force on the smaller one from the upper one? Now, this was our beginning of the semester. This is right from chapter 23, right at the beginning. So we just called this Coulomb's law right here at the beginning. Where's chapter 23? Okay, there we are finally. So there's 23, and section 3 right here is Coulomb's law. And on this page, it just says, look, just if you got 2 point charges, just put them together and multiply all of them. Now, maybe more appropriate might be, as we got a little more advanced, was in section 4 here, where we got into the electric field, and we said, well, maybe it's better to figure out what the electric field is and then put that second charge. Now, we only have a field from one charge, and then we would get the force. So here's the equation for the electric field. So I'm going to kind of do that in those 2 steps. Let's find the field first, and then multiply by the charge we're going to put in that field to get the force. And, of course, that is exactly the same thing as the easy case. But as you can see, there's a part B, and I suspect it's not quite as easy. So maybe we better go to the main idea of electric fields, not just electric forces. All right, so let's do our field first. And so how much field do I get from number 2 at this location of number 1? And so I would say E equals, and I would have this Coulomb's constant times the charge over R squared. So this would be 9 times 10 to the 9th. The charge would be 7.5, I think this is nanocoulombs. Microcoulombs, 10 to the minus 6. Glad I looked. Microcoulombs. That's going to be a lot of charge. So this might be huge forces. And the distance between them is the 0.00145 squared. Okay. So there is going to be our electric field. It's probably going to be pretty big. So 9 times 10 to the 9th. Where my dog's barking here. Let me go see here. All right, hopefully I will keep him quiet there. Okay, so then 7.5 times 10 to the negative 6. Then divide that by 0.00145 squared. And I'm looking at 3.21 times 10 to the 10th newtons per coulomb for the electric field. And so to finish at least part A, then we can get the force by saying how much charge you're going to put in that field. And so this is the other charge, 2.25 microcoulombs. And I'm going to put it in a field of 3.21 times 10 to the 10th newtons per coulomb. And get a force of times 2.25 times 10 to the micro. 6. And so this is going to give me a very large force. Let's call it 72,200 newtons. Okay. So again, that's kind of the easy part. B gets a little bit harder, but I hope it's looking a lot like we did in number 2, because we're just going to take what we already know is the field from a point, and we're going to add it up to get a rod. And so this right here would say, okay, what is the electric field from a rod? Because once I know that, I can just use this idea, that I would then be putting this charge in the field created by this rod. Now, again, like a lot of these problems, you could do it a short way, because we did this one in class. The book also did it. In fact, let me see if I can find, where did the book do this? It must have been somewhere in this section. There it is. Example 6. So example 6, it says, look, here's the field at point P from this rod of length L. And what they got after all their work is right here. Here is the electric field from a rod, where the A is the distance from the end of the rod to the point in question, and L is the length of the rod. So probably the best way to do this is to look at your notes from class, or to look at your textbook and say, all right, this is then the equation that I need. And that would be the shortest and fastest way to do it. But just like I did on number 1, where I decided to add up a bunch of rings to give you the potential of the cylinder, let's kind of go through this same logic and say, all right, you know, what if I had a rod, and I take this rod and I say, let's figure out what the electric field is some distance A away. I could think of each little chunk of this rod as having a charge dq, and then I could say the electric field from the rod is the summation of the little tiny electric field from a point. And of course, this was the main lesson of the second half of chapter 23, right? It was saying, okay, here's how you get the electric field from a rod. Here's how you get the electric field from a ring. And they just divided the ring into a bunch of points and added them up. Here they did the disk, where they then said, well, let's extend this idea. If we already know the equation for a disk, let's add up a bunch of disks in order to get, a bunch of rings in order to get the disk. And so that was kind of our beginning part of that. And I'm going to just kind of say the same thing here, that I could take the equation for a point, and if I think of a little point of charge as being dq, it's some distance away. Which, if you're going to add up a bunch of them and it's evenly distributed, we can use that idea of lambda again. A little bit of charge over a little bit of length. And so that little bit of charge would be that point charge over a little tiny microscopic length. And so this would be lambda dx when we move it to the other side to replace our dq. And then we're going to do an r squared. And then r in this case is just that distance away, x. And so there's no point in writing it as an r squared. It's just this x. How far away are we? If you measure x from this point, then x would start at a and then go to a plus l, because we are going to add up points. The first one being right here, which is a distance a away, and the last one is a plus l away. And so we would have to do this little integral. And like all of our integrations. We can figure out what things remain constant and pull them in front of the integral. And then we have a power function. In a power function, you just add 1 to the exponent. That makes negative 1 on the exponent, so I'll put it down here. And then you divide by that new one, which is negative 1, although I'll move it up at top. And then our limits were from a to a plus L. So this is Coulomb's constant times L, and then there'll be 1 minus a plus L, and then minus a negative 1 over a. Now, if we get a common denominator, we would have a plus L. And then up here, we'd be multiplying by a, so that'd be a negative a. Over here, we would be an a plus an L. And so we would then have Coulomb's constant times lambda times L times a, and then a plus L. Now, one more step, the lambda would be the whole charge divided by the whole length. And then so this L would cancel off, and you get your Coulomb's constant times Q over an A, and then an A plus an L, and that is this right up here. So again, this isn't necessary on the exam, but nonetheless, at the same time, I am a strong believer in not trying to memorize a bunch of equations. But on the other hand, these were worked out for us, and we've used them many times. And so we did it in the book, we did it in class, and so we had problems on it. So feel free then to say, okay, we did this in class. We've got the electric field from a rod. All right, so whether or not you start right here, or if you re-derive it from scratch, you're going to get this electric field. And that's the big step of this problem. All right, so the electric field would be, as I put in my numbers, maybe I'll put this on the screen like this. Okay. And so Coulomb's constant would be 9 times 10 to the 9th. Times the charge. I lost the problem now. And this is the whole charge, the 7.5 times 10 to the negative 6. We can divide that by A. A is the distance away, so 0.00145. We could also divide it by the A plus the L. So the L looks like it's 2 millimeters, and so A plus L looks like it's 3.45 millimeters, so 0.00345. All right, and so I get a field of 1.35 times 10 to the 10th newtons per coulomb here in my calculation. Now that I've taken this and made it more realistic, if you will, and given it, instead of being a point charge, spread out. Now, that being said, I would think that I should get a smaller field in this second part, B, than I got in A, because A, all the charge is this same distance away, but in B, a lot of it, is spread out further away. And so coming back to what we did in part A, we got 3.2 times 10 to the 10th. Now we get quite a bit less than that. So sure enough, it is a smaller field. And the last step is that easy step is like, okay, you are going to put the 2.25 times 10 to the minus 6 in this field of 1.35 times 10 to the 10th to get that force. So I already have the field in my calculator. Let me just take the 2.25 2.5 micro and get a force significantly lower, 30,000, I'll round it to 400. And so there is my force. Wait, did I do that right? I think I did it right. 2.25, wait, 1.35 times 10 to the 10th, okay, and then times a charge of 2.25, okay, good. And so there is my force. And that might be the end of B. Yep, what is the force on the upper charge? Nice. Okay, but again, hopefully you see how A is pretty straightforward, kind of a, I don't want to say too elementary one, but more of a plug and chug, and then a little more thinking with some calculus involved, and more realistic too. All right, let me call that quits, and then move on to the last problem. Let's see, the last problem says a slab of insulating material. All right, so this is like a plane that's got some thickness to it. It says infinite in two of its dimensions, but not its three. Has a uniform positively charged density of rho, and there's an edge view of it. And then what is the equation for the electric field? Now, maybe the hardest part of this problem is to recognize that this should be done with Gauss's law. This has a lot of symmetry. That's our argument. Symmetries, infinities. You really want to do Gauss's law. In fact, that was chapter 24. And I think this one is just a straight up copy out of the book. Yep, there it is, number 59. Well, okay, not nearly as hard as 59 because it doesn't keep going and have all these other pieces. It just says inside and outside. Okay, so not quite an exact copy, but pretty close, at least the idea of it. In fact, why don't I go back in the book and just say, why don't we repeat kind of what the author did here when they had a sheet. Now, their sheet didn't have any thickness to it, so it was always outside. So maybe that's the way to do first. That's actually part B. In this case, part B is easier because it's outside. And then let's just, copy this. This is an example number 5. And so we have, something where I'm going to do a Gaussian surface that extends like a cylinder. And again, I'll do B first. So these will be values of x that are greater than or equal to d over 2. See, the slab has a thickness of d, so anything greater than d over 2. And I should maybe do absolute value because it could be on that side also. But when you apply Gauss's law, which says the integral of E dot dA equals the charge inside over epsilon naught, this is where we can do those lines of symmetry. Let's see, I think in class I've been drawing them in red. I think I got a red pen around here somewhere. But this would be the lines of symmetry. You could, take this slab and draw any line across it. And so that would have to be the same as the direction of the electric field. So when you do a closed surface, there is this left cap. Then there is the right cap. And then there is the face. Do I have a piece of paper? If I do a little sticky here, And I don't know if this would illustrate it quite well. But if I'm doing, a closed surface like this where the paper is actually the what I'll call the face, and then there's a cap over here and a cap over here to be completely closed. But the thing about the face is we're going to get cosine of 90 degrees because the normal vector would be, pointing outward around this thing, and the electric field is going to be along its axis of symmetry. So that one goes to 0, which is really good because the other two, we would have cosine of 0 degrees and cosine of 0 degrees because the electric field would be pointing outward along the axis of symmetry, and then so is the normal vector. In fact, these two are the same. And so we could argue that we have twice just one of them. And one of them, the electric field would be the same on its entire surface. So you just get 2 times the electric field times the area of this cap. And that, of course, then is what example 24.5 did. It got 2EA. And then we have the charge inside. And the charge inside, let me just put epsilon on, is just going to be the charge density times the volume inside, but the volume where there is charge. And so there would only be charged in this little area here. And so that would be the area of one of these circles times D. And the two areas would cancel out. And so this electric field should be rho D over 2 epsilon naught. Yay! And since ours has thickness, that's where it differs a little bit than this example in the book. But I think you see the idea. It's still a charge inside. My difference here is charge inside. I did rho, which is charge per volume, so I'd have to multiply by volume. In the book example, they had right here, which was sigma times area, because it's surface charge times then a surface. Okay. And so this is the answer to B. What is the field on the outside? Now, the last part of this, since I did it out of order, would be A. And since I kind of made a mess of my picture, let me redraw it. Here's my slab, and I'm going to do a Gaussian surface on the inside. And if we place the origin right here, then this face is at X, and this face, or I should say cap, is at negative X. And the reason I'm doing that is because if I start here with Gauss's law, but this time I'm thinking about a Gaussian surface that's inside. See, last time I had Gauss's law, but I did where the caps went to the outside. Now the caps are going to be on the inside. But all the logic that we just did here for the caps is exactly the same. So this is just going to come out to be 2 times E times A also. There's really no difference. We still have these lines of symmetry. And so we still have a 90 degrees between the normal and the electric field, or the lines of symmetry on the face, and we still have a left and right, each having an angle of 0, so they're going to be the same. That's where the 2 comes from, and then we just have the electric field times the area, because electric field's a constant, and blah, blah, blah. So that is exactly the same logic and the same procedure. What does change, though, is on the inside, we would have density And just like over here, we had density, and this was the volume where there was charge. And so it wasn't the volume of the whole Gaussian surface. Here, we would want the volume of the whole Gaussian surface, which doesn't go all the way out to D. In fact, the volume of this Gaussian surface would be its surface area times a 2x. That's the length of this thing. Length of this thing is 2x. And so the volume would be its length times its area. And so that's really the only difference between A and B. So number 5 here might be the easiest one on the exam, or at least the shortest one. And then a 2 cancels off, and then an A cancels off. And you end up with the equation for the electric field as rho x over epsilon naught. Which I do believe, if you were doing some extra homework problems and you got to this one, yeah, it even says show that this is true. This is part A of the problem. And then it goes to some other stuff that's much harder, so we didn't do that for the test. But it does have that first part, the Gaussian surface. And in fact, you could even argue then that the inside and outside should match right on the surface. So right on the surface here, my distance, my x, would equal d over 2. So if I put in d over 2, that is the equation right at the surface, but it's also the equation that we just got on the outside, and so it does match on the outside here. What did I do with my part A? Oh yeah, part A was on this sheet here. Yeah, and so good, makes me feel good that they match at the boundary. And so in other words, this says the field gets bigger, reaches some maximum at the boundary, and then as we get outside, this is just saying it stays the same, that maximum value all the way on the outside. All right. Well, I hope you did well, and I hope you also learned a lot from any mistakes you might have made, and therefore you won't make them again as we move forward into the other chapters. All right. Take care.